Thank you, everyone. I know this is probably the hardest part of the two-day conference in the afternoon, a little bit after lunch. I promise I'll try to keep it entertaining and keep you all awake. No guarantees. So we'll get right to it. So this is the session. I'm going to be talking about security precognition using chaos engineering as applied to cybersecurity. I'm going to talk about a number of different use cases you can actually apply chaos engineering to cybersecurity. Actually, I argue there are more from a security lens than from the availability, traditional chaos engineering availability use cases. But I'm going to focus predominantly on incident response, but I may touch on some of the other use cases. It just helps if I focus on the use case you all can get sort of the how-to and the sort of the problems around that we're trying to solve. This is the company I work for. I co-founded Verica about 6 months ago with Casey Rosenthal. If you are familiar with chaos engineering, you may recognize that name. He was part of creating it. He wrote the book on it. He's the CEO of the company. Okay, so I'm going to talk about security precognition. And I'll explain a little bit more about what that means. But I want to first start by polling the audience. How many people here have actually heard of Chaos Monkey? Okay. Who's heard of chaos engineering? You know, the number's always different. It's so funny, right? It's the same thing, right? Chaos Monkey is just, arguably, chaos engineering is a domain of practice. Has been around probably 3 to 4 years. That's really when the O'Reilly book came out, I think, 2.5 years ago, the original O'Reilly. There's actually another O'Reilly book soon to be released in the fall. There will be a whole chapter on security in that book. Chaos Monkey has been around for almost 10 years. It began as part of Netflix's, as Adrian Calcroft was talking about yesterday, Netflix's cloud transformation from data center to AWS. It's kind of funny that a lot of people talk about I can't do chaos engineering. That's too difficult for us. So the chaos is normal, is my normal operating procedure at work. But actually, Netflix, the need for chaos engineering was actually born out of Netflix's cloud transformation. So this is one of my favorite quotes on resilience engineering from John Allspaw. He's one of the pioneers in modern resilience engineering, at least resilience engineering is applied to what we do as builders and breakers of code. But John Allspaw likes to say that resilience is the story of the outage that never happened. I'll talk a little bit about how that relates to precognition. So a little bit about me. I am the CTO of Verica, a stealthy startup. It's not so stealthy, if you guys know the name. But I'm the former chief security architect of all of United Health Group. United Health Group, if you're not familiar with it, is the largest healthcare company in the world. It's about 400 different companies, $300 billion company a year. Lots of challenges, lots of problems there. It's also part of what rose the need for chaos engineering, and I'm going to talk about how I use chaos engineering to solve what I needed as the architect, the ivory tower architect at United. While at the company, I led, with a group of folks, I led the DevOps transformation at the company. I also led the open source transformation there as well. Actually, Chaos Slinger, which is the first open source tool that applies chaos engineering to cybersecurity, the tool we wrote there was the first open source tool for the company. For a background at NASA, DHS, I'm a frequent speaker in chaos engineering and frequent author. So if there's material I didn't cover very deep here, there's a bunch of talks on the internet as well as a bunch of articles and books that I've written. You guys can check that out. I'll point you to it. So in this session, I will cover a lot of things in the next 35 to 40 minutes. So that's what this means. Okay, let's get started. So fundamentally, our systems have evolved beyond the human ability to mentally model their behavior. So who here has actually seen the Death Star diagrams? You seen these before? Okay. Well, what's happening is, actually, this is everyone now. This is no longer just Google, Amazon, and Netflix. So if you've never seen one of the Death Star diagrams, each dot represents a microservice. So pretty complex, huh? So the point here to recognize is that we're building systems and that are delivering more and more value to our customers quicker. We're also introducing a sheer scale, speed, and complexity of delivery of that value that is making it very difficult for us to fundamentally understand what is happening at any given point in time in the system. So case in point, so this is actually a piece of software called Visceral. The other name of it is Flux, written by Netflix, written by Casey's chaos engineering team at Netflix. The idea of this is that, to take away from this is actually just a GIF, but it's a piece of software, is that it's very difficult for a human at any given point in time in here to understand what is going on. And with chaos engineering, you're not only concerned with a failure event on one node. What you're really concerned with is how that failure causes cascading failures and ripples throughout the rest of the system. So, how are we building systems today? Well, like I said before, things like all of these components, from continuous delivery to cloud computing, CI/CD, immutable infrastructure, microservices, automation, blue-greens, are very indicative also and related to the value. The reason why we're doing these things is we're able to, experiment with new features and functions with different parts of the user base and really determine whether the customer is getting value from it or not, and quickly deliver bug fixes and functions. But it is creating a very complex ecosystem when it comes to understanding failure events and system behavior. Well, the problem is when it comes to security. I used this phrase a couple months ago, and it seemed to stick with people, is that I have found, I spent a majority of my career as a software engineer before I got into security. And my observation is that security is so often concerned with catching up, they're not keeping up with technology. There's a significant gap between what techniques in engineering we're delivering today and the security that the security technologies in engineering that is needed to keep pace. So our solutions are still mostly monolithic in nature. It's not entirely true, but predominantly we're still monolithic from a design perspective. DevSecOps is catching on, but still not widely adopted. Our systems typically are expert-type systems that require some kind of formal knowledge around a tool. If you want to pick up a Palo Alto firewall or a Cisco ASA firewall, you need training. You need specialized knowledge in order to do that. And that's what I mean by requires domain knowledge. And we still think that the problem is actually around the adversary, around the criminal attacks. And I've actually done the research in this space, and I can explain why it's not. So what is the answer with all this complexity? Do we simplify? Well, the problem with software is that it only ever increases in complexity. Okay, is that and it's getting more and more difficult. Is that over the past 20 years we've continually abstracted and simplified, but at the end of the day, it's still ones and zeros. How well? So I want to pose a question: who here has ever actually seen a line of code execute? I mean, actually ever seen the code execute? I mean, it's not really to test your technical acumen. It's really to prove a point that, like, how well do you really understand how your system functions, okay? It was a great Dr. Richard Cook, I think, said, he said, do you need the monitor or does the computer? You need it, right? So the point is that there's layers of representation of how we perceive the computer, but there's actually how the computer functions. Those are two different things. Okay, so the point in this slide is to show the levels of abstraction. So there's a paper written in 1986 called No Silver Bullet. It describes where complexity comes from in software. There are really two domains of complexity in software. One is essential complexity, and the other is accidental complexity. So essential complexity comes from things like Conway's Law. So Conway's Law essentially states that organizations are destined to design systems that reflect the way they communicate. When I worked at United Health Group, and I'm sure where you work, you communicate a certain way because that's the way you do business, whether it be good or bad. But the way you communicate, the way you do business is the reason why you were successful. And that, when it comes to building software, is very difficult to extrapolate that away from the complexity of the software without changing the nature of the business. So you kind of are dealing with that by default. Accidental complexity comes through the complexity we add as part of the building process. What's the point of talking about complexity in terms of chaos engineering? Well, chaos engineering, believe it or not, is actually one of the only proactive methods you can actually determine, break apart the complexity and understand problems before they manifest into outages and incidents. So this is a quote from Dr. David Woods. As the complexity of a system increases, the accuracy of any single agent's own model of that system decreases. So the complexity of the systems I've been describing, the hard part here is that our systems are so big and change so often and are such a scale, it's difficult for us to mentally model what's happening versus what we think is happening versus how it's actually happening in reality. There's a gap. So the point is, how well do you really understand how your system works? Well, like I said, it's very difficult to grok this, right? And how do you know how your system works? Well, typically, all we ever really see is footsteps in the sand. What I mean by that is tracing, things like stack traces, things like log events. But it's very difficult when you have thousands of microservices, or even hundreds, to mentally understand. Just think about this as a model. Let's say you have an application. Let's say a healthcare application. So there's claims, there's payments, there's RX, whatever. Let's say there's 10 APIs, or 10 microservices. Well, you don't ever actually have 10. You actually probably have 6 to 10 of each for throughput reasons. You're probably running older versions and newer versions because you're doing blue-greens, you're testing out new functionality. But you've got to keep older versions of the microservice so other microservices can maintain their functionality. The problem is you're starting to see already the complexity here is that you could have 30, 40, 50 of each microservice, and now you have 400, 500 microservices now facilitating what used to be, you thought, is a very simple application. Not to mention the team models get more complicated. I think Randy Schaup talked a little bit about that in his talk yesterday. But the team model is getting complicated. Each team has a different. Each microservice has a different team. Those teams are each delivering functionality 10 times a day. So now you have a sheer speed of change within each part of the system and complexity on how they're actually being delivered and operated. And that's how this manifests. This is actually a picture of one of Netflix's edge services. So what does all this good stuff have to do with security? Well, the reality is that failure happens, and security is no different than any other part of the system. I love it when people focus so much, like because I spent my career has foundations in different areas of engineering, meaning the network engineering, system engineering, and mostly software engineering before I got into security. I never saw security and the rest of the system as two different things. I don't believe in different classes of system when it comes to design. There is one system. We can't look at security as something separate. When it comes to failure, security is no different. And I argue, if you fundamentally don't understand how your system works to begin with, how do you expect the security to be any different? Okay, so I want to talk a bit about failure here. So these are some obvious failures. I mean, when are the airlines not going down? But how many people are familiar with the Amazon Prime outage last year? Anybody? No? Okay. Well, Amazon was down for 3 hours. We'll try to guess how much that cost Amazon for being down for 3 hours? In dollars, US dollars. What do you think? A couple million? Anyone else? $100 million for 3 hours. $100 million. United Health Group, when I worked there, during open enrollment, it was roughly about $1 million a minute when we were down. So this stuff is serious, and it costs a lot of money when we're down. But it goes beyond dollars, okay? How many people are familiar with this one? Inbound ICBM comes as a text message on your phone. I'd be freaking out if I saw that, But the reality here is this could have been. So this was the people of Hawaii got a text message from the government saying an inbound ballistic missile was coming their way. Okay, this was actually incorrect. It was a malformed message. But this kind of stuff can be prevented. But here's the real problem in articulating and understanding this failure, is that what happens if this happens again? For real? Are people going to take that seriously? That's the real. So failure goes beyond dollars and cents. It comes down to people's lives as well. So like I said, incidents and outages are expensive. Let's talk about security incidents, okay? Security incidents, no matter how much you prepare, how much money you spend, how many people you have, how if you got the best and greatest security capabilities, you still don't know very much, right? You still don't know when it's going to happen, why it's happening, who's going to do it, how they're doing it, so it's incidents are very subjective in nature. But let's face it, when incidents happen, when incidents and outages happen, people freak out. When you get a call from the security incident response team and talking about a incident in your app, the conditions by which you're thinking and operating and feeling put your mind in a state where it's not clear. You're not clear. They're most likely, they're just trying to figure out what's going on as well. But people do this. People literally do this. I mean, they may not physically do that, but in their minds, that's kind of how people think. And it's important to recognize that, okay? As a result, people spend too much time reacting to outages instead of building more resilient systems, instead of learning from them. Some of the greatest ways to improve your systems actually are coming through this data, but you're not taking the time to actually understand why problems are manifesting. So when it comes to incident response is the problem with incident response. It's not proactive. We're waiting for a problem to happen before we fix it. Okay? So chaos engineering. So chaos engineering, by definition, is the discipline of experimentation on a distributed system to build confidence in the system's ability to withstand turbulent conditions. So I'm going to talk more about how this kind of applies. But most people are familiar with Chaos Monkey. Chaos Monkey, like I said, was born out of Netflix's cloud transformation to Amazon Web Services. Remember, a long time ago, Amazon was actually DVDs and CDs that came to you in the mail. But what was happening is a unique feature of Amazon Web Services at the time, due to Netflix's scale. Even at the beginning of Netflix's streaming, they were about 35% of all North American internet. Now they're over 45% of worldwide internet is Netflix, worldwide. That's a heavy engineering footprint, both on our brittle TCP/IP networks, as well as on Amazon Web Services. But a unique feature at the time when they were building their streaming platforms is that instances and AMIs would just disappear. They couldn't figure out why. It would just disappear. That was causing a disruption, obviously, for the business. And so what they decided is, okay, well, this is not going to go very well for us if we cannot be resilient to this kind of failure. So what they did is they built a tool called Chaos Monkey, and they would proactively bring down, everyone knew this was happening. This was not secret. Everyone knew that your service could be subjected to Chaos Monkey bringing down pseudo-randomly. It may not be your day. Tomorrow may be your day where your service gets brought down. But the fact that that could happen any day, any time was on engineers' minds, right? Is that your service is subject to this kind of failure. You must build your services to be resilient to this type of problem. It turns out engineers are really good at solving well-defined problems. What chaos engineering did, or what Chaos Monkey in particular, is it helped provide additional context and understanding about the failures that could happen to be solved proactively. So CHAP, a lot of people don't know about CHAP. Anybody know about CHAP? Ah, we got a couple chaos engineering nerds. Okay, cool. So CHAP has actually never been open source. I may or may not know of a company that is bringing this to market. But this is actually the tool that Netflix runs, 10 to 20,000 experiments a day. The reason why it was never open source is an integration piece of software. If you're familiar with integration software, it's only valuable to actually having those integrations. So it's only valuable to Netflix. But Verica, we may or may not be bringing that to market as a commercial solution in the near time frame. Sorry, my mic was messing up. So essentially, what does CHAP do? So CHAP provides an automated platform for running experiments safely, but the safety is the key part. So through using things like auto canaries and proxies, what it does is CHAP will proactively introspect the microservice architecture, and it will look for interesting heuristics like, I don't know, like a service is closer to the edge, or a service has more requests, or it will determine which services are kind of interesting and important, and it will proactively take two copies of it. One will be labeled a control, another an experiment, and it will siphon off anywhere from 0.01 to 0.05% of real traffic. And on the control, we just pass the traffic along to the next service. But on the experiment, we do something interesting. That's where we do our chaos engineering. That's where we do, we ratchet up latency up until the SLO, or we misconfigure a port, we flop a database connection, those kinds of things. But when you never, a key point about chaos engineering is you never do chaos engineering on something you expect to fail. You're not going to get any value from instrumenting something you already know to not work, okay? So when you do chaos engineering, you're not expecting a failure here. You're expecting what you thought, your hypothesis about your system. So I believe if latency were to, I don't know, be ratcheted up to just below the SLO, the service is able to respond to that kind of activity, and there would not be a failure, right? That is your assumption. But CHAP is here. What CHAP does is the event that actually causes the fact you're actually not true. And what's funny about chaos engineering is most people who try an experiment for the first time, they're almost always wrong. I've actually never seen anybody be right about how they thought their system worked. So who's doing chaos engineering? I track a little over 1,000 companies now that are really doing it. There's a maturity curve. There's companies that sort of just getting started with game day exercises. They're fiddling with Chaos Monkey or the Chaos Toolkit. Both are great tools to check out. There's Cube Monkey as well. I talked to some folks that were using Cube Monkey with Kubernetes. But quite a few companies now. And what's interesting is that, I don't know, some of these are Silicon Valley companies, but a lot of them aren't. So important thing to recognize, before you get started with chaos engineering, I highly recommend you read the O'Reilly books. They're kind of good context for you to understand a basis. But this is the doctrine. This is what we all live by in chaos engineering. This is the rule set. This is like the golden law, at least the way I see it, is that you got to understand the principles of chaos. It helps you walk through how to kind of do it and the constraints you need to follow as far as scope and scale and maturing your practice. Okay, so security chaos engineering, what is that? Okay, so let's come back to the fact that people operate differently when they expect things to fail. In fact, the normal condition of your system is to fail, okay? But this is what happens. So people operate differently when they expect things to fail, okay? When an outage happens, this is what happens, right? But what if we didn't wait till an outage happened to learn about our systems, right? What if we learned about them when we're operating like this, right? Things are happy. Okay, there's a difference, right? This one or that one? This one or that one? Okay. We do chaos engineering here, okay? When there's not an outage, when there's not an incident, when there's not an outage. What usually happens when there's an outage or an incident is that, like I said, people freak out, okay? And within, I don't know, 10 to 30-minute window, the CEO will get a phone call, right? Or you get a phone call from the CEO saying that, why are we down? We're losing money. Get that thing back up and running now. So the focus is about getting it back up and running now. It's not about learning about what really happened or not. So we focus on getting it back up and running, reinstated, and then we do our postmortem. And there's several problems wrong with that. And I'll talk about that in a minute. So the normal condition of not only humans, but the systems and things we build is failure, flat out. Cindy Decker once said that our systems are not safe by default. Humans make them that way. Same way with security. Systems are not secure by default. We always blame humans, right? Well, humans are the reason why the system exists, or it's secure, or it's safe. So it's important to recognize we are both sides of the equation. And in fact, our systems are this way as well, but we as humans, we need failure to learn and grow. It's a key component to getting better at things. So with chaos engineering, we're essentially flipping the model, okay? Our postmortem, instead of being an after-action exercise, which, come on, postmortems are usually pretty difficult to do anyway. Everything looks different in hindsight. After it's happened, oh yeah, duh, it was the load balancer. It wasn't all the other humans and systems that were involved way earlier in the equation that caused it. It was that one thing. What's interesting about root cause is the root cause is actually somewhat of a fallacy. I'll explain to you why. Is that, think about the company you work for, okay? Can you think about one root cause why the company is successful? You can't, right? Because you say, oh, well, our products, we have great engineers, or we got a great management team, or it's for the same reason why you can't think of one reason why something's successful is the same reason why you can't think of why it's not. So it's important to recognize when you reach a root cause in your investigation, that is the beginning of the investigation. That's not the end. Okay. So what's often happening is you're writing something down as a root cause. You're just moving on. But the real goal, the real data, the real reasons why the system failed were further upstream. So chaos engineering is not actually about causing chaos. A lot of people I get that twisted, is that so focused on, aren't you injecting failure into the system? Well, yeah. Well, we're trying to flush out the failure. The failure is already inherent in your system. If you operate a system today that does not fail at least once a day or has not failed in a long time, I would go back and be very concerned about that system. So one of the ways that I use chaos engineering in security was to drive objective feedback loops about how effective my security was. So as the chief security architect of United Health Group, I was always worried about the ivory tower syndrome. So people would come to me, they'd ask me for solutions. Aaron, how do I secure this thing or that thing? What control do I use? What capability do I use? And I was never sure how effective it actually was. I would say something and then they would go do it. I felt like, as a builder myself, like, people need more context than that for actually be effective. And I was concerned that what I gave them was not actually being implemented or used the way it should have been. And so one of the things I used chaos engineering for was to develop a series of hypotheses about how the security should function in certain scenarios and cause those scenarios. Cause the expectation by which I expected the controls to trigger, if that makes sense. So I'm going to go through an example with Chaos Slinger here in a second so you get a better idea what that is. So some of the value we got from using chaos engineering for security was we validated our runbooks. If you think about it, you don't really know how good your runbooks are until there is an incident. It's very difficult to compare even incidents of similar nature when they're on different systems, different ecosystems, and validate how effective your steps in your runbooks are. So we were really able to, because we caused the incident, we caused the failure, we caused the signal in the system, we weren't guessing about what we thought happened. We were able to manage, to measure, to understand, do we have the right skills? Did we have the right tools and technologies? Did we have enough people? Those sorts of things, and were the runbooks correct? So important distinction here. Sometimes people read too much into this, but we like to, the chaos engineering community likes to describe instrumentation in two domains, testing and experimentation. Granted, there is a form of testing that is, experimentation is very similar to testing. But the point is that testing in general is focused on the fact that you'll go in looking for something, information you're already aware of. So what I mean by that is you're trying to validate something you already know to be true or false. Meaning, like in security, it's like a CVE or an attack pattern or a vulnerability. Whereas experimentation, the point of experimentation is to drive new information that you did not know, new insights. And there's a few differences. I always get this question from people, what is the difference between pen testing, red teaming, purple teaming? And so there's lots of differences. I wrote an article. This is the cool graphic I made. But this whole article describes in detail all the differences. As a certified pen tester myself, a lot of times the pen tests are very point in time. There is a need for manual techniques, but even the automated pen testing techniques are very noisy. If you remember the picture of the visceral graph I showed up here, in that environment, a lot of times the automated pen testing tools, they need to so to do a Node.js mass assignment attack, it's gonna try to guess at lots of different things to see if they're there before it actually does multi-step type of attack. What happens is when you're making that much noise, it's very difficult to ascertain what failed and what didn't throughout the rest of the system. So chaos engineering is a very small in scope sort of technique where it's about injecting one failure at a time and understanding that failure, because you're not just trying to understand the failure on that one endpoint. You're trying to determine the cascading failure as well. You're trying to understand what else happened in the ecosystem. So it's mostly focused on, small in scope, cascading events. So I want to bring up a couple things and I'll get to chaos layer. So an important thing to recognize here, so this is Podimon report, if anybody's familiar with that. Do I have any security people here? Oh, cool. All right. So the Podimon report is pretty common in the security community when it comes to data breaches, cost of a data breach, how much it'll cost the company. But it's important to look at this. This data has actually been the same since the life of Podimon. I had to do this research as part of writing the chapter for the O'Reilly book. But if you look at look at the data. So 48% of data breaches, are said to be caused by malicious or criminal attacks. This is the sexy stuff. This is the Russian FSB attacking, or this is the NSA writing malware. This is the spy versus spy cool movie stuff, right? Well, what's funny about this actually is if you look at this, these numbers the ratios have roughly been about the same for the last 10 years. But 52% of the overall equation is actually of the reasons why data breaches are caused are due to human error and system glitches. What does that even mean, right? So system glitches are really, there's really no good definition in the Podimon report when they define it. It can mean so many things. But really what it came down to is the understanding is that it's a lack of understanding of why an error happened. So that's one, is a system glitch. And two, human error. So first and foremost, human error is not a thing. Humans, just error. It's just being human, okay? And so these are determined to be root causes. So I hope that some of this is being coming together for you. Is that? But I want to point out one big thing here, is that I argue how many, if we focus more on this side of the equation, how much of this would actually be successful? We're causing these problems, okay? And if you've ever looked at a piece of malware, if anybody's ever broke down a piece of malware, I mean, in general, there's probably about 5 to 6%, anywhere from 4 to 6%. I'm kind of making up those numbers, but those are rough numbers. I'd say 4 to 6% of actual malware is sophisticated stuff, very good code, very that's dangerous stuff. but the rest of it is just crap, right? That code should never, ever execute. The reality of it is, because we don't focus on this, we're so concerned about 0 days and APTs and being attacked, that we're not focusing on the fact that we're creating the ability for the attack to be successful. So security chaos engineering is actually about getting rid of the low-hanging fruit that we create, the accidents, the mistakes. So as a software engineer, I was often asked to create new things that never existed before. Well, sometimes when you do that, shit happens. You make mistakes, and those mistakes are costly. But that's where security chaos engineering is focused on. It's focused on introducing mistakes into the system that you expect to catch, to stop, to block, to prevent, to understand how effective those things you put in place actually are, and also learn about what other things you did not know were effective already. So let's get to Chaos Slinger. So we're down to 4 minutes here. So it's about building confidence when it actually works, okay? So John Oswald likes to say that we need to stop looking for better answers. Everybody's got an AI or an ML solution to just solve everything for you anymore. But we need to stop actually looking for better answers and do the due diligence and start asking better questions. So what is the system doing? Has it done this before? Why is it behaving in that way? And what is it supposed to do next? Oh yeah, and how did it get into the state? So, okay, and now I'm getting to Chaos Slinger here. I want to cover that for you. So how does my security really work? And what evidence do I have to prove it? So Chaos Slinger is the first open source tool. I think Adrian might have mentioned this in his talk yesterday. It's the first ever tool that applies the concepts of sort of Chaos Monkey. We actually broke down the Go code in Chaos Monkey and sort of realized we didn't actually need any of that code. Most of it is cloud native anymore. Actually, the real name, there's a different real name of Chaos Slinger, but it was not PC, so we could not use that name. Essentially, what Chaos Slinger is it's a series of Lambda functions. It's completely native AWS in nature. And essentially, it's a framework for building and executing security chaos experiments. And in the GitHub repo, there is an explanation of kind of an architecture on how it works, how it functions, how you're supposed to write. If you do contribute to Chaos Slinger, it's important for the code to be accepted to actually write documentation, or they won't accept it. I don't work at United Health Group anymore, so. Anyway, so the main example experiment in Chaos Slinger, the first one we wrote, was actually a misconfigured or unauthorized port change. The reason why we chose that is pretty much everybody, no matter where you stand, whether you're a manager, whether you're a security person or a software engineer, everybody kind of understands what a firewall is supposed to do or what it does. I mean, they've been around for a long time. So we used that as an example. So essentially, whether it be malicious in nature, it be accidental, there's lots of ways a misconfigured port, it happens a lot, by the way, but there's lots of ways it can manifest. It could be that somebody filled out a form wrong or a change ticket wrong. It could be that somebody applied the change wrong. It could be that somebody needed the change and couldn't get it fast enough and applied it manually themselves. But either way, what happens is that if a misconfigured port or a port that's not supposed to be open gets opened, as a security person, we expect lots of bells and whistles and lights and alarms just to go off, right? That should actually never execute. It should never be successful. But what's interesting is when we started doing this in AWS United, is that what we realized is our very expensive firewalls we put in place actually didn't, it wasn't every other time, it was kind of intermittent, but it was almost every other time the firewall actually did not catch it. But what was really interesting is that, this is where we learned new information, is that the Cloud Native Configuration Management tool caught it every time, caught and blocked the change. So that was kind of fundamental for us, is that this thing we're not really even paying for, we're getting for free almost, is doing more than the $200 million Palo Alto firewall that we put out there. It was interesting. It taught us new things about how our security really functioned versus how we thought it functioned. And that was important. Taught us a good lesson. And what's also interesting is that because the hypothesis was disproved, both the Palo Alto firewall and the configuration management tool, you expect to send good log data to a log tool or like a SIM SIEM is a security incident and event management tool. It's like a log tool for security. But you expect alert to fire off when that happens. But what happened actually is when the alerts fired off, it went to our operations center. The ops people did not actually know where it came from. They could tell the alert came from AWS, but they couldn't ascertain whether it was actually the commercial AWS or non-commercial, because United Health Group has a series of commercial software offerings. So that was as an interesting finding because had that actually been a real incident, that could have taken anywhere from 30 minutes to 5 hours to figure out through the elastic IPs and through things like SNAT to try to figure out where it actually came from. And during an outage, we don't have 5 hours. We don't have 30 minutes. Okay? But what was great is the world was not on fire. People were not freaking out. People were inquisitive. They're asking. They were seeking more quality, seeking to try to learn more about why this was happening. When there's an outage, there's no time for that. It's about getting it back up. It's not about learning. Chaos engineering is about building a learning culture around system behavior and failure. And I will tell you, if you take the journey, if you go down the journey, I'm telling you, you will learn so many interesting things and ways to improve your system. I think we're still at the dawn of chaos engineering, but I would love to hear your stories. So my contact information, I'll put it back up here. Oh, here's some more experiment examples, but I think that's all the time I have.
Thank you, Aaron.
Thank you.
And where can we find more about Chaos Slinger? Can you tell us about that?
Chaos Slinger, you can just type in the name or you could just contact me. I love following up and talking to people and helping, but it's on GitHub.
Cool. So we have a few minutes left for the Q&A session. Everyone, you can hit up slido.com and upvote the existing questions or ask your own ones. First, I want to start with this one. It's a joke question, but I'm going to indulge. Let me bring up my best Jeff Goldblum impression here, because I'm glad that Ian Malcolm found a way all the way from Jurassic Park to here. Living systems are never in an equilibrium. They are inherently unstable. They may seem stable, but they are not. Is that true?
That is so awesome of an explanation. But that's true. It's true. It's very true. I mean, actually, I didn't cover this, but I didn't have time really to cover complex adaptive systems. This is actually applied physics, is when it comes down to it. The human body, weather patterns, financial markets, nation-state political interactions are actually complex adaptive systems. Systems always changing. And that's where chaos theory comes from, is the fact that you're not worried about the initial impact or the initial effect of a cause. You're worried about the responses and changes throughout the rest of the system and how that ripples and manifests weird, non-linear behavior.
Amazing. So it was actually a relevant question.
Very relevant. It's great. It was
Thanks.
great. It was good.
So let's see the next question. What's the best way to get started with chaos engineering within your organization?
So I get this one a lot. I actually got this one from a gentleman here in the audience yesterday. And the best way to get started is through a game day. But you want to do chaos engineering eyes wide open during business hours. You want to be transparent with your management. And one of the ways you can justify and explain why there's a need for it, because that's always something you need to do, and you explain the ROI and the value, is that go to your past incident and outage data. Okay, because you're having outages all the time, and they're getting worse. I don't even need to know where you work to know that. When this is happening to Google, Facebook, there's a massive outage. I think Facebook, Google, and can't remember who else were down for like 8 hours earlier this year. When some of those advanced engineering companies in the world have this problem, you're having this problem too. So that's a great way to explain sort of the value, is look at what has happened previously and say, hey, we want to try to understand this so this doesn't happen again. So, game day exercises. Sorry, I didn't fully answer that question. Game day exercises are the best way to get started. That is sort of manual chaos engineering. We get all the right people in the room, and you actually develop a hypothesis, inject the failure, and try to determine whether or not your hypothesis was true or not.
Perfect, thank you.
Yeah.
How do you run chaos experiments often enough to cope with an ever-changing system?
Oh my gosh, I've never gotten this question, but what a great question.
Really?
I don't know. I mean, Casey Rosenthal might have a better answer to this question, or Nora Jones. They're both former Netflixers. What I would say is you can't run them often enough. is that with this problem, we have no tools in this toolbox. So if you ever heard of observability, it's sort of a movement around that now. Observability is sort of it focuses on better ways to understand the behavior of our systems through things like logging, tracing, visual tools like Visceral. You guys saw the Visceral tool I showed you. If that was all in code or in log events, you couldn't grok what was going on. The point of having a visual is so you can see, oh, that's a failure. Oh, it's easier for us to kind of mentally model that using that piece. But how often? I don't know. I think that's probably indicative of the organization you work for. But I guess where I was coming from earlier is that we don't have we don't have enough tools to solve this complex adaptive system problem. We need new, more innovative ways to understand system behavior so we can prevent these bad things from happening.
All right, we have a short time for the last question.
Sure.
Would you run the experimentation on production systems? If so, how would you limit user impact? That's a great question.
So this is a great question also. These are all great questions. So would you run the experiment on production systems? Well, the outage in instance is going to happen on production, sadly enough. But you can get value from running on QA and test. You can still learn a lot of things there. They're actually, I'm not going to mention the nature of the business, but they're actually a business that said, well, we can't run chaos engineering on prod because we're going to have too many important things. But we're going to do it in QA. I told this example to some other people yesterday, is that they decided to run, bring down Kafka. They brought down a Kafka cluster, and what happened is that Kafka cluster went down. They expected a new one to be spun up, and it sort of maintained its operations. So they're like, okay, we're going to do this on QA. They went forth and did it in a game day exercise, and guess what happened? Anybody guess? Production went down, right? If you don't understand the value of chaos engineering through that example, they're getting clearer than that. They didn't understand throughout time on that system, they had slowly created a weird dependency on QA. But that kind of stuff happens. So, yeah.
Thank you. I'm going to let you get rid of that annoying headset.
Yeah,
but before that, let me present you the gift on behalf of the craft organizers.
Thank you very much.
Thank you, Aaron.
Thank you, everyone.
Please give it up for Aaron Rinehart.
Thank you. Thank you.